Good morning. Um, so the topic I chose for my embedded project is 3D IC design and challenges, a literature review. So this is an overview of my presentation. So first I want to go through what a 3D IC is, and then I want to go through the timeline a little bit, and then I want to discuss about 3D IC clock design, floor planning, power ground network design, fabrication, thermal aware design, and interconnection networks. So 3D IC is a chip in which various 2D chips are placed on top of each other and then connected by means of a vertical TSV. TSV is a metal wire which helps us to connect various layers of a 3D chip. So let's consider the figure on the left. We have 4 dies. Let's say we have a 2D IC. What we do is we split that up into 4 equal halves and then place them on top of each other and connect them by means of a TSV. So this is an example of a 3D integrated circuit. It has power TSVs, it has signal TSVs, it also has like a test signal TSVs. So this shows a 3D circuit with a bunch of CPUs, a bunch of special purpose coprocessors and memory, and they are connected together. So this shows the timeline of 3D ICs. So 3D ICs came into existence when silicon on insulator was first developed in the 1980s or the 1990s. So the goals of my paper and my project is to present a survey on existing techniques to develop 3D ICs and suggest various trade-offs between various design parameters that we can keep in mind when we actually do a 3D IC design. And I also want to discuss various design techniques for designing power clock interconnects. I want to go over thermal aware designs, and I also want to cover a little bit of fabrication cost. So first, let's start with 3D IC clock design. So the first work, or some of the works regarding clock designs, were proposed which included having a bunch of clock buffers in some cases, or in Arunachalam's work he has a separate layer of clock networks, and there was this other paper which included which utilizes buffers, and it also takes temperature into account when it does the clock design or when it places clock TSVs. So Kim improved on the previous work by reducing the number of buffers, and he also does not have any kind of control signal, so that was a much simpler algorithm which distributes the clock in a very smart way. So all the works that deal with clock design has to do with designing a clock with 0 clock skew. So there was this work in 7 which proposed a 0 clock skew tree. They have a tool called ZCTE3D for solving the 0 clock skew 3D problem. So that's about clock designs. Coming to floor planning design and tools, there are a bunch of papers which extend the concept of 2D floor planning into 3D, and then Lee in his paper proposed a 3D floor planning model that included dynamic thermal effects. So in this case, his work is actually based on the idea that the packing in the Z direction is not going to be the same as in X or Y direction because there are no vertical transistors, and he makes use of a bucket and 2D array representation and he does various operations like rotating it or swapping it or reversing it, moving it, or moving an object between various layers based on their thermal profiles and so on and so forth. and comes up with an optimal design which provides a much greater thermal temperature reduction. So there was this other paper which also does pretty much a similar thing. By Hung, he also has like similar instructions like node swap, rotating, moving, resizing, and so on and so forth. And the advantage of Hung's tool over the previous work is that this tool actually also plots the temperature profile, and this is extended by including a variable number of additional levels, each composed of so they also plot the temperature profiles of each and every layer, which allow us to have a much detailed analysis on various layers and their profiles. Alright, so now coming to the power ground network. Power ground network is one of the most important design things that we have to keep in mind when we do 3D IC design, because most of the areas that of the 3D IC design is actually being occupied by the TSVs, or so the power TSVs do occupy a much bigger area in a 3D chip, and so we have to be careful on how we are going to utilize the power ground network area in a chip. So there are two concerns here. One of them is a power supply noise. To reduce the power supply noise, we could use some decoupling capacitors to reduce power supply noise. And another design parameter that we have to take care of when we actually do power network design is that if we do not supply enough power to our chip, then there is an internal resistance drop, which causes like a much bigger performance degradation. So that's something to keep in mind when we do power ground network design. So Lee implemented a power ground distribution design based on a grid structure, and then there was this other paper by Z in which he actually co-synthesizes both the power distribution network and the floor plan, and he makes use of a simulated annealing approach to actually formulate and solve an optimization problem that solves power and floor plan together to end up with an optimal design. And this is an example of a power ground network. And then fabrication cost is another important thing that we have to take care of when we do any design, because we want to know if design of 3D chips is actually worth doing it. So there are a lot of extra costs that comes into the picture when we go from 2D to 3D. Like the wafer cost might be a little bit higher because it also depends on what type of process node we use and what size of wafer we use, and also it also depends on the number of layers we have. And then the bonding cost is a little bit higher because in this case we have to consider the cost for bonding different layers of the 3D chip together. So that's an added cost. And then there's also the cooling cost. So the cooling cost is one of the most important ones. In case of 2D, we do not usually need an effective cooling solution, but with 3D, because of very high power density, the temperatures in the same chip is going to be much higher than its 2D counterpart, and so we have to take in we might have to implement effective cooling solutions if the temperature gets too high. So that could be a significantly added cost. So now that said, let's go and look into thermal aware design. So a lot of designs that we do in 3D IC has to be thermally aware, because that's a very critical problem in 3D chip implementation. So Kong proposed this thermal aware placement approach based on a transformation approach. So he uses a bunch of transformation techniques to convert a 2D placement problem into a 3D placement problem and perform optimal placement. And then Goso, in his first work, 22, actually considers the thermal profile of various modules in a 3D chip, or in a single layer of a 3D chip, and then he measures the temperatures of these modules, and his algorithm makes sure that the temperatures are not too high. And in his next work, 23, he actually performs placement. The algorithm is still similar. He uses a 3D matrix which has thermal profiles of various objects in a 3D chip, and then he first arranges these objects among various layers in such a way that the area is more or less the same, and he then calculates the thermal profile of every 2D matrix which corresponds to every layer of the 3D chip, and then he formulates an optimization problem which tries to minimize every submatrix of that big layers, so that their sum is minimized, or in other words, the peak temperature is minimized. The next important thing to consider in a 3D IC chip design is the design of interconnection networks. So whenever we design something, we need to make sure that the yield is good, so that otherwise the design is fruitless. So in order to make sure that the yield of our design is good, we have to make sure that the interconnection networks does not have a shard on it, or it's not open anywhere. So there are tests which tries to figure out whether the interconnection network that is being designed is okay. And so Huang proposed this self-repair scheme to actually figure out the interconnect faults. And this is his algorithm flow. So there is a circuit which actually detects the interconnect fault, and then based on its output, it determines whether it has to repair it, or it could pass on to the next module. So it's a pretty basic algorithm for detecting interconnect faults. And there's this other paper which is by Chi, which proposes a design for test scheme that can detect faulty interconnects in a 3D IC. And for interconnect testing, they use true complement algorithm. Each interconnect receives a different test patterns. So they have like a counting sequence. So consider the first two numbers to the left of the counting sequence, which is the complement of that sequence. So let's say we have like a four interconnects, and they are represented by 0, 0, 0, 1, 1, 0, and 1, 1. So the data that is being sent to each interconnect is the number 0, 0 and its complement 1, 1. So 0, 0 is the entry to the right, and 1, 1 is the entry to the left. And if for some reason there is a fault, then it can be identified by making sure that by figuring out that whether it is stuck at 0 or whether it gives the same response. If it gives the same response, it's a short or it's a open. So to conclude the work, we saw a lot of techniques and challenges in 3D ICs, and we discussed a lot of design techniques for power, clock, floor planning, thermal aware designs, interconnection networks. And these are the list of references. And thanks.